Welcome to Module 203F on cooling systems. Now that we're familiar with the components of a cooling system, we're going to see how they all work together in order to achieve the cooling that we need. The challenge to refrigerating air is how to take a room temperature vapor and make it so cold that it sucks all the heat out of the air around it. There are many changes that need to happen to the refrigerant in order to accomplish this. We need to change the temperature from hot to cool to cold and then back to warm. We need to change the state from liquid to vapor and back again, and we also need to change the pressure from high and then back down to low again. Each step in the cycle requires the refrigerant to meet different conditions. The physics principle that this system relies on is that evaporating liquid will draw heat from its surroundings, and the mechanical cooling system controls that evaporation, and it all starts with the compressor. Inside the compressor, we have warm, low-pressure vapor that comes into it from our house. The compressor's job is therefore to increase the pressure of that vapor. As the pressure increases, we are jamming more of the refrigerant into the same space, which creates more molecular friction, which creates a lot of heat. Anytime that we add pressure, we also add heat. The result is we have a high temperature, high pressure vapor output. So the compressor is responsible for two things. It changes the refrigerant from a low to high pressure, and in doing so, it also changes the refrigerant from a low to a high temperature. However, the state of the refrigerant stays as a vapor. The next step is to take that hot, high pressure vapor that comes out of the compressor and start putting it into the condensing coil. The coil has a fan which helps the hot vapor shed the heat to the surrounding air. The refrigerant is going to change its state as it goes through the condensing coil. As it loses its heat, it turns from a vapor down into a liquid. The result is that my output is now a warm, high pressure liquid. So the condensing coil is responsible for two things. It changes it from a hot to warm temperature, so it cools it down, and changes the state from a vapor to a liquid. But the pressure inside the condensing coil is going to be the exact same pressure as it was when it came out of the compressor. The next step is having that warm, high pressure liquid going from the condensing coil into the expansion valve. And the amount of refrigerant that is in the expansion valve is controlled by the temperature of the evaporator coil input. This makes sure that the system doesn't freeze. The expansion valve changes the pressure inside by changing the size of the tubing between the input and the output. And now the high pressure liquid being released into a low pressure environment will significantly lower its temperature. And the temperature drop is approximate to the temperature rise that we saw inside the compressor. This results in an output that is a cold, low pressure liquid. So the expansion valve is responsible for two things. It changes the refrigerant from a high pressure to low pressure, and that results in changing from a warm to a cold temperature, but it stays in the liquid state. Lastly, the refrigerant goes into the evaporator coil. This is placed in the upper air plenum of the furnace, and the furnace fan is interlocked with the air conditioning unit to circulate the house air through the evaporator coil. The cold liquid refrigerant from the expansion valve enters the evaporator coil, and since the refrigerant is so much colder, it pulls a lot of heat from the surrounding air. The house air enters the plenum warm, but leaves the plenum cold. As heat is being transferred from the air to the refrigerant, it changes state from a liquid back to a vapor again. After the evaporator coil, now the refrigerant makes its way back to my compressor, which starts the cycle all over again. All four of my primary components are responsible for two changes to the refrigerant. Make sure you are familiar with what changes happen at which component and also know what to expect for the input and the output of each component as well. When it comes to the electrical side of an air cooling unit, we can look at the schematic diagram for a rooftop unit. On here we can see both the low voltage control circuit as well as the power circuit. In the low voltage control circuit on the bottom of the screen, we can see the three different points of our thermostat being R, G, and Y. R is our source, G is our fan, Y is our cooling. We also see the thermostat contact that is going to be automated depending on the temperature of the room. There's also a high pressure and low pressure switch that are in line with the contactor. And when we have a call for cooling, we have the switch closed on the R, the thermostat will close, and that will activate both the indoor fan relay, as well as go through the high and low pressure switch to turn on the contactor. On my power side, my contactor is going to control my compressor as well as my condenser fan motor out inside my unit. And I will have a set of contacts on both the line 1 and the line 2 side. We also have a control from the indoor fan relay to control the indoor fan motor, which would be our furnace motor. This way, when the system calls for cool, I have two relays that engage. I have the contactor relay, and I also have the indoor fan relay. The indoor fan relay will control my indoor fan, my contactor relay will control my compressor, and the fan outside inside the air conditioner unit. Due to the compressor and the motor that's inside it, we need to consider motor code rules as well. Rule 28604 Subrule 5 states that we need to have the disconnecting means for the air conditioning equipment within sight and within 3 meters of the equipment. But also keep in mind, if you place the disconnect directly behind where the air conditioner is going, it may not be accessible. So make sure that you place it in a smart location that you want to work on it. 28200 states that we must have its own branch circuit for the air conditioner, so it cannot share a circuit with anything else. And 28106 states what the wire size for it shall be, which is not less than 125% of the full load current rating of the motor. The purpose of this is because we have what's called an inrush current when that motor starts, so our conductor must be able to handle that. For our low voltage wiring, it should be 18 gauge, but that is up to a maximum of 35 meters. If we go longer than 35 meters, we have to upsize our gauge for our control wiring to 16 gauge because of voltage drop that's associated with the distance. You have now reached the end of this objective. Review your module, complete the knowledge check, and then continue on to the next video.